3, 2, 1. Liftoff. 32 minutes past the hour. Liftoff.
What do you do when you want to observe somewhere so deep in space that you can never reach it? You send a space observation station. NASA has done precisely that by sending the James Webb Space Telescope to deep space so that it can help us see more of our universe.
There are no limits to the human spirit. I thought I would see the end of physics, but now I think the wonder of discovery will continue long after I am gone.
One of the places the Space Telescope will be pointed at is the very edge of the universe. The findings at the edge of the universe promises to be scary. What will the first telescope see at the edge of the universe? How does it affect you personally? Join us as we explore the terrifying discovery by the James Webb Space Telescope at the edge of the universe that changes everything. Now that the James Webb Space Telescope has made it to its orbit and work to get it up and running has started, how capable exactly is it? How powerful is this new eye in space? Well, according to NASA, the JWST is so sensitive to infrared light, it would be able to detect even the slightest heat of a bumblebee at the distance of the moon. To quantify it better, this telescope is 100 times more powerful than the iconic Hubble telescope that has been serving us great pictures of the universe for more than 3 decades. The JWST is intended to take baby pictures of the universe, literally. Sure, the Hubble can take breathtaking photos of space, but it has its limits. For instance, it hasn't allowed scientists to see the first galaxies formed after the Big Bang. Webb will change that because it will be acting like a giant time machine. It's like we have this 14-billion-year-old story of the universe, but we're missing that first chapter. The JWST will capture light that has been traversing the cosmos for as long as 13.5 billion years, extending our views of the universe several hundred million years earlier than the Hubble. What makes the Webb telescope so powerful? Part of it is the giant primary mirror, 6.4 meters in diameter. It comprises 18 smaller segments that must align perfectly. The segments are covered in a gold coating so thin that a single strand of human hair is 1,000 times thicker. The less than 2 ounces of 24-karat gold reflect infrared light better than other metals. Infrared is just outside the visible spectrum of what humans can see. Actually, the mirrors are not solid gold, they are made of beryllium. To function correctly, the Webb telescope needs to be kept cool. It does that thanks to a 5-layer sun shield the size of a tennis court. This mechanism was folded up when Webb launched on Christmas Day, but less than 2 weeks later, the extremely thin layers of the shield were successfully deployed. Without the shield, the immense heat from the sun would overwhelm the telescope's sensors. The side facing the sun will experience about 260 degrees Fahrenheit, while the other side will be chilled to some 370 degrees below zero, a nearly 600-degree difference. The sun shield gives Webb the equivalent sun protection factor, or SPF, of 1 million. One thing that makes scientists nervous about the Webb telescope is that they won't be able to fix any issues that arise, both during the launch and operation. For comparison, in Hubble's lifetime, 5 space shuttle crews have made service calls to correct the telescope's initial blurry vision and perform maintenance and upgrades. But that is because the Hubble is only 340 miles away. The Webb telescope is much farther away, nearly 1 million miles away. This is far beyond the reach of spacewalking repair crews, so NASA only got one chance to get it right. However, if the proper technology is developed, scientists could someday send a robot to refuel Webb, extending its life. Speaking of fuel, NASA initially thought the telescope would last only 10 years, but thanks to an efficient launch, there is enough fuel left to power the JWST for 20 years. For now, scientists are eagerly awaiting Webb's first photos, which will arrive this summer. After that, the JWST will settle down to work. It will help to investigate the nature of dark energy in the universe and understand the nature of these very old objects. It will also help to search if there is another Earth out there among the distant exoplanets that litter the universe. Interestingly, the JWST has started proving its worth almost $10 billion even before taking its first photos. Northrop Grumman, which built the telescope's mirrors, had to cover new ground because a precise mirror had never been created. The technology the company invented is now being used by eye surgeons. They also developed stuff on the computer level. The company made huge advances in understanding how to deploy big things, like how to take a giant sun shield the size of a tennis court and fold it up neatly and deploy it. Now, when astronomers try to see the edge of the universe with the JWST, what will they see? Humans have always been interested in what surrounds us, but traveling across the universe isn't just traveling through space, but through time as well. But before we get on, we need to establish something, the dimension of the universe, because to find the edge, we should first know the dimensions of the universe. Our universe is expected to be 13.772 billion years old, making it quite old. So how big is our universe really? Scientists today estimate it to be 28.5 gigaparsecs in width. Getting a grasp of how big that figure is requires some basics of astronomical units. How large is a parsec? To understand how a parsec is defined, you should first know what an astronomical unit, AU, is. 1 AU is essentially the average distance between the Sun and the Earth, approximately 150 million kilometers. So a parsec is defined as the longest length of a triangle whose shortest side is 1 AU, and which subtends an angle of 1 arcsecond at the opposite vertex. If you calculate further, you will see that 1 parsec equals 3.26 light years, or the distance light travels in 1 year, which is about 9,460 billion kilometers. And we are talking about 28 gigaparsecs here, which is 93 billion light years. That is 879,780 times 10 raised to the power of 18 kilometers. That is just unimaginably huge. For comparison, the length of DNA of all humans on Earth combined together, when stretched, will be about 0.119 billion light years long. Now, look at the figures mentioned earlier carefully, and you'll discover that something looks inconsistent. The speed of light is the absolute maximum speed possible, right? So if the universe is 13.7 billion years old, how come the width of the universe is about 93 billion light years? Technically, if an object created just after the Big Bang moved with the speed of light, it should by now have traveled a maximum of, what? 13.7 billion light years, nothing more, nothing less. From where did all the matter come from beyond this limit? This is where we turn to Hubble's law. The law states that objects observed in deep space are found to be redshifted. Redshift refers to the shifting of the wavelength of light to the red end of the spectrum, that is, an increase in the wavelength of the light. But why does the wavelength expand? One reason, space is expanding. And this is not just that objects are moving away from one another, but the fabric of space itself is expanding. Here is where everything goes crazy. The expansion is accelerating. It is assumed that dark matter and dark energy have a strong influence on this behavior. So the extra distance due to the expansion of space needs to be taken into account when estimating the width of the universe. This is why the edge of the universe is clearly not at some 13 billion light years from Earth. It is estimated to be much beyond that. What is the furthest astronomical object humans can see? One thing is that there are some objects in the universe that we might never see. Why? About 16 billion light years from Earth, this marks the current cosmic event horizon of the universe. Are we there yet? Nope, not yet. This distance is the upper limit of light ever reaching us if it originated at that distance today. This implies beyond 16 billion light years, the expansion of space is faster than the speed of light itself. Obviously, the light will never reach us as it will have to travel through a relatively expanding space. This also signifies that any event that may have happened today beyond the cosmic event horizon will not be observable by us, no matter what. But we can see even further through telescopes like the JWST. The most distant galaxy ever observed is the GNZ11, located about 32 billion light years away from Earth. Mind you, we calculate this distance taking into account the expansion of space as well. At about 46 billion light years away from Earth, we reach what is called the surface of last scattering. This is what you will observe irrespective of the direction you look at. The surface of last scattering is like a uniform sphere of fog from which the first ever photons of cosmic microwave background radiation came after recombination and photon decoupling. Contrary to the name, it's the origin of the very first scattering of light, but the last of what we can observe. Is this finally the edge of the universe? Yes and no. Technically, this is the farthest point in space and the farthest in time that we can observe. That essentially forms the edge of the observable universe. What lies even beyond that is what is known as the opaque universe. This marks the limit of what we can observe, but not what we can imagine. Let us now go even beyond the edge of the observable universe. What can exist there? All this time, we have only explored what existed at a point in space in the distant past. A more unimaginable question would be, what could possibly exist there at present? The edge of the observable universe also marks what is called the particle horizon, the maximum distance one can see into the past. Everything we have seen so far was from the perspective of keeping Earth at the center and scaling time to the past with distance. This brings us to the question, is the universe infinite? Well, from Einstein's theory of relativity, it can be estimated directly that a flat universe must be infinite. Can we then conclude there is no edge or end to the universe? It is not so straightforward. We have not been able to determine categorically if the universe is finite or not. Let's hear what you think of the edge of the universe in the comments section.